We proceed to our next example for the analysis of indeterminate frames using virtual work method. So for example, we have this truss loaded with 24 kilonewtons at joint D. So first, we are to determine the degree of indeterminacy. So we have the number of bars plus the number of support reactions. Is it greater than or less than or equal to twice the number of joints? So as you can see, how many bars do we have? So 1, 2, 3, 4 plus, okay, truss AD and BCR pass through. So on this section, we don't have a joint, so we are just passing through. So we have the number of bars. We have 6 plus, okay, we have A. So let's assume that its vertical reaction is upward, A vertical. Assuming that its horizontal reaction is to the left, A vertical, and since we have C as a roller support, we have only one reaction. That is the same C horizontal. So how many reactions? We have 3 reactions plus the number of is it equal or less than or greater than twice of number of joints? How many joints? 1, 2, 3, 4. So this is twice the number of joints, 2 times 4. So you have this is 9 is obviously greater than 8. So we have the degree of indeterminacy is first degree, 9 minus 8. As you can see, we can compute for the support reactions. We have 3 equations of equilibrium and we have 3 support reactions, which means what causes the indeterminacy? We have an excess. Okay, so we have an excess bar. We have an excess bar member of the given truss, which means we can categorize this truss as indeterminate. And this truss is indeterminate internally. It is indeterminate internally for a reason. What causes the indeterminacy? We have an excess bar member. Okay, so we may compute for the support reactions. As you can see, we can compute. It is the support reactions can be computed. That is by summation of forces vertical equal to 0. We have the only vertical resistance is the A vertical, the vertical reaction at point A. That is the same as 24 kilonewtons. Okay, then we can do summation moment at A equal to 0, clockwise moments to be positive. That will be the same as 24. This is 24 times 4, okay, minus the horizontal reaction at C times 3. And this is equal to 0. So we have the horizontal reaction at C. This is 24 over 3 is 8 times 4. 8 times 4 is 32 kilonewtons. And by summation of forces, horizontal equal to 0, to the right forces to be positive. So that is CH, we have 32 minus A vertical, this should be A horizontal. Minus A horizontal equal to 0. So we have A horizontal is equal to the same as 32 kilonewtons. So CH is to the right. AH is to the left. So we have this support reactions. So again, our next step is we are to assign a redundant. So again, this is a truss which is indeterminate internally. What causes the indeterminacy? An excess bar member. So we may choose one. So we may choose, let's say, we can have AD or BC. So let us assign our redundant. So our redundant will be BC. So we are choosing BC as the redundant. Okay, so then we have the compatibility equation. So our compatibility equation, that is the delta, the deflection of the truss due to real load, plus we have F, the deflection of the truss or the primary truss due to unit load, then this is the redundant equal to 0. So again, we have the delta is the summation of the actual force due to real load multiplied by the actual force due to unit load times the length, and this is divided by AE. And we have F, this is the summation of the actual load due to unit load multiplied by the actual load due to unit load times the length divided by AE. Okay, so if we are to remove, for example, we are now removing member BC. Okay, that makes this truss a determinate truss. So it is already determinate. We assume that AE is constant. Okay, so let us compute for the bar forces due to real loads. Okay, so let us compute for the axial forces for all the members due to the real loads. But again, we remove member BC to make this truss a determinate truss. Let us start with joint C. At joint C, we have the horizontal reaction of 32 kilonewtons, which is computed a while ago. So I assume that CD will be under compression. Obviously, they are collinear, so the value of the horizontal reaction CH will be the same as the axial force for member CD, equal to 32 kilonewtons, and this is under compression. And at joint C, as you can see, we don't have a vertical force. That makes the axial force for member AC to be, okay, this is a 0 bar force member. And then we may proceed to joint A. Again, this is obvious since at joint A, may isa pa tayong member. This is, obviously this is under tension. This is member AD. Okay, so I think this is not really obvious. So at joint A, we have the vertical reaction of 20, this is supposed to be 24 kilonewtons. AH, that is 32 kilonewtons to the left. So we have member ABN. Member AC is 0, a 0 bar force member, and I assume that AD will be under tension. This is summation of forces, vertical equal to 0, upward forces to be positive. So this is the same, I think the slope is 3 vertical, 4 horizontal. So that is, we have 24 minus the axial force for member AD. Vertical component is 3 over 4 equal to 0. We have the axial force for member AD. Supposedly this is not 3 over 4. Vertical component is 3 over 5. So we have 40, this is 40 kilonewtons, and AD is under tension. Okay, then we have AB. This is by summation of forces, horizontal equal to 0, to the right forces to be positive. So this is AD. What is the axial force for AD? We have 40. Horizontal component of 40, that is the same as 4 over 5 minus, we have AH is 32 kilonewtons minus the axial force for member AB equal to 0. So you have the axial force for member AB. So what is the 4 over 5 of 40? It's 32 minus 32. That makes member AB to be a 0 force member. So AB is also 0. So those are the axial forces due to due to reload. Lastly, meron pa pala tayong isa dito. We have at joint D. I think this one will be also obvious. Since member AB is a zero force member, it is expected that BD will also be a zero force member. So let us just check. This is by summation of forces, vertical equal to 0, upward forces to be positive. We have that is 40, vertical component is 3 over 5, minus 24, minus the actual force for member BD equal to 0. So we have BD, what is 40 divided by 5 is 8, times 3 is 24, minus 24 is 0. So that makes member BD will be 0. So these are the actual forces due to reload. So let us compute the actual forces due to 1 unit load. We are replacing BC with a 1 unit load. So our next step, we remove the reload, apply on this or acting on this truss. Since our selected redundant is member BC, we replace it with a 1 unit load. Since we have an internal loading 1 kilonewton, we assume that the support reactions will be equal to 0. So support reactions are 0. So I think this is a bit obvious. We have 1 kilonewton as a diagonal member, which is similar to member AD. So we have BC is similar to member AD. That is the same as 1 kilonewton, and this is expected to be under tension. In the same way, member AB is similar to member CD, and member AC is similar to member BD. So we may choose one joint, then we can have, I think the actual force for all the members due to the 1 unit load. So we have, let us choose joint B. So I'll be assuming that member AB and member BD, the actual forces will be under compression. So let us do summation of forces, vertical equal to 0, upward forces to be positive. That is member BD, vertical up, minus the vertical component of the 1 unit load. This is 1 unit, vertical component is 3 over 5 equal to 0. So we have actual force for member BD. Again, member BD is similar to member AC. So we have them as 0.6 and they are under compression. So BD and AC. Then we do summation of forces, horizontal equal to 0, to the right forces to be positive. That is, we have AB. A minus horizontal component is 4 over 5 of the 1 unit load equal to 0. So we have member AB. Member AB is similar to member CD. We have that is 0.8, and this is also under compression. So these are the actual forces due to 1 unit load. So let us tabulate the values. So these are this is the table for all the values. So we have axial forces due to real loads, the axial force due to unit load, then their corresponding length. So again, percent convention, members under compression, negative, members under tension, we have a positive sign. So let's determine those values. The product of the axial load or axial force due to real load multiplied by the axial force due to the unit load, that is from the redundant BC, multiplied by the length. So since this is 0, so we have 0, and this is also 0. Then we have this is negative 32 multiplied by negative 32 multiplied by 0.8 multiplied by 4. So we have that value as positive 102.4. Then this is 0. And we have 40 times 1 times 5. So we have 40 times 5 is 200. And lastly, this is we have 0. So we have the summation. The summation of the axial force due to real load, the axial force due to unit load, the length, this is divided by AE. That is the same as 102.4 plus 200. So that will give us the value of 300. I think this is 302.4. This is equivalent of delta, the deflection of the truss due to real loads. Then we have the axial force due to unit load multiplied by the axial force due to unit load times the length. So we have this is 0.8, negative 0.8 squared times 4 is equal to 2.56. And then we have this is negative 0.6 squared divided by 3. And we have 1. This is 1.08. And these two are the same. Negative 0.8 squared times 4 is equal to 2.56. Alright, the next, BD and AC, the same. We have 0.6 squared times 3, that is 1.08. Then we have this is 1 times 1 or 1 squared times 5. We have this is 5. And lastly, we have 1 squared. That's 5 is the same as 5. So let's have the summation. This is the summation of the axial force due to unit load multiplied by the axial force due to unit load times the length. This is divided by AE. And that will be equal to, we have 2.56. How many 2.56 there? We have 2 plus 1.08. We have also 2. Then 10. And that will give us the value of 17.28, and this is equal to the deflection of the primary truss due to the unit load. So this is these two are both divided by AE. So from our compatibility equation, we have delta plus F multiplied by the redundant is now equal to 0. So we have the value. This is 302.4 divided by AE, plus F, we have that is 17.28. This is divided by AE multiplied by the redundant equal to 0. So we have the redundant equal to that will be equal to negative 17.5 kilonewton. So again, what does this negative sign indicates? So initially, we assume BC, the 1 unit load, if you can still recall, the 1 unit load is assumed to be under tension. We assume member BC to be under tension, the redundant. But if we are to arrive with the negative sign, it only means that we have a wrong assumption that member BC, this BC, which is equal to the redundant, equal to 17.5 kilonewtons, and it should be under compression. So member BC should be under compression. Okay? So let us compute for the other actual, let us compute for the actual bar force of the other members. Okay, so let's compute for the actual force of the other bar members. So we have the equation. The actual bar force equal to the actual force due to real load plus U, that is the actual force due to the unit load, multiplied by the redundant. So we have, let's say, first we have AB. So we have the actual force for member AB is equal to, the bar force is 0, equal to, what is it, corresponding unit load? That is equal to negative. We have negative 0.80. What is our redundant? Negative 17.5. So we have the actual bar force for member AB is equal to negative 0.8 multiplied by negative 17.5. So that makes it positive 14. And this is 14 kilonewtons. If it is positive, it only means that it is under tension. That is for member AB. How about, let's try CD. So let's say this is the actual force for member CD equal to the actual force due to real load plus the actual force due to unit load times the redundant. The actual bar force for member CD, okay, bar force for member CD we have negative 32. This is negative 32 plus corresponding unit load for CD is negative 0.8. Okay, multiplied by the redundant, this is negative 17.5. So we'll be having the actual bar force for member CD. Okay, that is equal to negative 18. Negative 18 kilonewtons. That only means that this member is under compression. Okay, so we have AB, this is 14 kilonewtons under tension. How about BD? Okay, BD, we have 0, this is negative 0.6 multiplied by negative 17.5. We have, this is 10.5 under tension. And then we have CD. We computed for CD. That is equal to negative 18. And this is negative 18 kilonewtons for CD. How about for AC? Again, that is 0. So we have 0.6. The same, I think, AC is the same as BD. So that is 0.6 times 17.5. That is the same as positive 10.5 under, also under tension. Then we have, for member AD, that is, we have 40, a 40 plus, we have 1, that is 1 times negative 17.5, the actual force will be equal to 22.5, positive, which means this is under tension, and we have BC, that is our redundant, the negative 17.5. So these are the actual bar forces of our example. Okay, so